In this section, I'm going to guide you on how to graph the tangent and cotangent functions. They're very similar as far as approach to graphing the sine and cosine, but of course their graphs are different. We're still going to use important points on the graph to be able to graph them in an easier fashion. So let's first talk about some of the characteristics of them. The tangent function is what we're going to start with first. And the domain of the tangent function, since tangent is defined as sine over cosine, cosine is the denominator of tangent. So whenever cosine is 0, the value of tangent is undefined. So that happens at a bunch of these intervals, and those intervals are drawn by these dashed or dotted lines. Those are going to be called asymptotes. And therefore, the domain for this is all values of x such that x is not one of those values. And those values are odd values of pi over 2. And n is an integer. And the range, it covers every y value. So the range would be from negative infinity to infinity. And if you use the sine and cosine values from the unit circle, right, you could figure out the function value of tangent for these 5 values. Now remember, at the pi halves for this one, the value is undefined. But at negative pi fourths, 0, and pi fourths, the values are negative 1, 0, and 1. And those 3 values are what we're going to use to help us graph this function. This graph is discontinuous at values of x of the form x equals 2n plus 1 times pi halves, where n is an integer. And at every one of those discontinuities, we call those vertical asymptotes. So it's very important that we know where the asymptotes are. The x-intercepts are where it crosses the x-axis. And for these, they cross at every integer value of pi. So n times pi, and n is an integer. If you look at this graph right here between negative pi halves and pi halves, that means the period has a value of pi. There are no minimum or maximum values, so its graph has no amplitude. This graph is symmetric with respect to the origin. So symmetry with respect to the origin implies an odd function. And by the definition of an odd function, all x's in the domain are equivalent to this. The tangent of negative x is equal to the negative tangent of positive x. And so let's look at a similar discussion for cotangent now. So look at the way cotangent looks now as compared to the tangent. It still has some discontinuities like tangent did, but now the discontinuities are not at pi halves, they're at integer values of pi. So this domain is all values of x that are not equal to multiple values of pi, where n is an integer. The range is still the same from negative infinity to infinity. This graph is also discontinuous. At values of x of the form x equals n pi, and has vertical asymptotes at these values. I forgot to fill in the values for y here. Again, the values of the corners are undefined for this one. And since cotangent is the inverse of tangent, we reverse the values that we got before. So before for tangent, we had -1, 0, 1. So for this one, it's going to be +1, 0, -1. Okay. So if you recall, tangent had intercepts that were these x equals n pi, but these are now the vertical asymptotes, and the vertical asymptotes of tangent are now the x-intercepts of cotangent. So they're going to look like this, where n is an integer. Its period still the same, it's still pi. There are no minimum or maximum values, so it has no amplitude. The graph is symmetric with respect to the origin as well, and therefore it is an odd function. And therefore, the cotangent of -x is equivalent to the negative cotangent of +x. Okay, so please note the similarities and the differences between the two graphs. Let's now look at a technique for graphing these. So if you're going to graph a times tangent of bx, or y equals a cotangent of bx, where b is positive, we're going to follow these steps. We're first going to find the period. So if b is greater than 0, we're gonna take the original period and divide it by b, and that'll give us the period of the function. Then we gotta find the vertical asymptotes for one period of the function. And for tangent, you would let the argument bx, this one, equal to plus or minus pi halves. So negative pi halves and pi halves. So where you find it useful, you can say bx is equal to plus or minus pi halves, and then solve that equation. And you might see me use that in a problem or two today. And then for cotangent, we just did cotangent is the original period is from 0 to pi. So we let bx equals 0 and bx equals pi. And then you would solve those two different equations to give you the two asymptotes. We would then sketch the vertical asymptotes, determine the interval that we're going to use, and just like we did for sine and cosine, we would separate that into 4 equal parts by dividing the distance of the interval by 4. And then we would evaluate the function for those midpoints that I told you, the 1, the 0, and the -1, and then plot those points with a smooth curve. And if we have to, we extend the value out to more than one period, okay? All right, let's give it a shot. All right, let's start with this one here. So the graph is y equals tangent of 2x. Since that 2 is in front of the x, we first use that to find the period. So the period is pi divided by 2. And then we got to find the two asymptotes. So we're going to say 2x is equal to plus or minus pi halves. And then if we divide by 2, we get the value of the asymptotes, which is plus or minus pi fourths. Okay, those are the two asymptotes that I already graphed them right here at positive pi fourths and at negative pi fourths. So the interval in question is the interval between negative pi fourths and pi fourths. And the length of that interval, you subtract pi fourths minus negative pi fourths, which gives you 2 pi fourths, which is pi halves. So the length of that interval is pi halves, And then you want to split that into 4 equal intervals. So you divide that by 4, and that'll give you pi over 8, the distance of each subinterval. So your 4 or your 5, if you count the first one, endpoints are from negative pi 4s, and then you add pi 8s to that, which will give you negative pi 8s, and then add pi 8s to that, which is 0, and then pi 8s, and then finally pi 4s. Okay, and then we use a similar approach that we did for sine and cosine, where we find the values of the important points on the graph. So that's what I'm going to do right now. So I'm going to find the value of x first, and then 2x, and then take the tangent of 2x. And hopefully you can catch on. This is pretty simple. So this, and remember that the endpoints are not necessary because those are at the asymptotes. So we get an undefined statement for those. So I'm only going to use the middle 3. So negative pi over 8, and then 0, and then pi 4s. So if you multiply that by 2, that'll give you negative pi 4s, 0, and I'm sorry, this was pi over 8. Then this will be positive pi 4s. And then those values are the ones that are from the previous sheet where I gave you the values of negative 1, 0, and 1. So these right here are your x values that you're going to plot, and these down here are the y values. Okay, and I'm going to plot them now. So negative pi 8's negative 1. So this will be my first plot, and then 0, 0, and then pi 8's positive 1. And I made myself some lines there to help me graph it, just because you know, my vision is not great, and I want to get as precise as I can. That's why I drew the 1s and the negative 1 with the dotted mark there. But now you connect it with a smooth curve, and as smooth as you can. And this is our first graph, the tangent of 2x. Again, we should mention because of the 2, the original period is cut in half. And before, the traditional period would be between negative pi halves and positive pi halves. So this one should be half of that, which is between negative pi 4s and positive pi 4s. All right, let's continue with another one. So this is a negative 3 tangent of 1/2 x. So let's find the period for this one. So that'll be pi divided by b. B is 1/2. So pi divided by 1/2 is 2 pi. Okay, and then your asymptotes you have 2x equals plus or minus 2 pi. And divide by 2. So x equals plus or minus pi. And so those are my asymptotes. They're right here. And so the interval in question is between negative pi and pi. Its length is 2 pi, and therefore the endpoints are going to be from negative pi to negative pi halves to 0 to pi halves and pi. And so for those three in the middle, we're going to find the function value that's equivalent to those. And so we're going to go like this. We're going to say x, and then 1/2 x, and then take the tangent of that, and then multiply it by -3. Okay, so the three values are negative pi halves, 0, and pi halves. And then you get half of that, so that's negative pi fourths, 0, and positive pi fourths. And then you take the tangent of those, and that would be -1, 0, 1. And then finally you multiply it by -3. So that'll be 3, 0, and -3. Okay. And if I plot it now, so again, these are my x values, and these are my y values. Okay. And so negative pi halves, +3 would be about right here. And then 0, 0. And then pi halves, -3. So about right there. And so something like that. And remember the 1/2 changed the period, but the -3 in the front made it flip or reflect over the x-axis. So now it's pointing in opposite directions as opposed to the traditional tangent function. All right, let's continue with another example. Let's look at the cotangent now. So once again, we want to find the period. So the period is pi divided by b. In this case, b is 2, so pi divided by 2. But unlike the tangent, remember we got to find the asymptotes by making 2x equals 0 and 2x equals pi. So when you divide this by 2, you still get 0. And then this one, you get pi halves. So at 0 and pi halves, so there's an asymptote right here on the y-axis. I didn't mark it, but it's the y-axis, and then the other asymptote is at pi halves right here. Okay. And so your interval of interest is between 0 and pi halves. And if you divide that by 4, that would be pi over 8. So if you start at 0 and then keep adding pi over 8, you will get 0, pi over 8, pi over 4, 3 pi over 8, and pi over 2. Okay. So these three right here that I'm going to use, those are the x values I'm going to use. And then if I take the cotangent of those, right? I would multiply those by 2, and then if I take the cotangent of those three, I would get 1, 0, -1, right? And then get half of that. So I'm abbreviating this without the table. Then you get half of those because in the function, we got to multiply it by a half. So that'll be 1/2, 0, -1/2. And those are going to be my y values now that I'm going to plot. So if I plot those, so pi 8's 1/2 is right here. 0, 0. And then 3 pi 8's -1/2. And if I connect that, we get our graph right here. So hopefully you're catching on the procedure, how to do these. This procedure will always work if you find the interval and then find the middle three values to help you graph the type of graph that you're doing. Now you still got to know what the tangent and cotangent look like and what happens if you if you reflected about the x-axis and any other transformation that we covered before. There is one more we covered before that I haven't done here, and that's a translation. Let's look at that one right now. So like this one right here. So notice the x minus pi 4s, that means it got translated to the right pi 4s. The minus in front of the cotangent means it was reflected about the x-axis. And then the -2 means it was translated downward by a factor of 2. Okay, so let me write that right here. So the period in this case is just pi because there's no number in front of the x. So the period is pi, right? But that -4 means there's a phase shift. So it means a phase shift. Sorry, I misspelled it. Phase shift of pi 4s to the right. Okay, and then the minus in front of the cotangent means a reflection about the x-axis. And then the -2 in the front means a translation down 2 units. So it is important that you know what these mean before you even work on them. Translation down 2 units. So that when you graph it, it supports what you already know. All right, so let's find the asymptotes. So we let each one of those x minus pi 4s first equals 0 and then equals pi. So if I solve for each one, this will give me pi 4s, and this will give me 5 pi 4s. So my interval in question is from pi 4s to 5 pi 4s. And that interval is a length of pi, because 5 pi 4s divided by pi 4s is 4 pi 4s, and which is pi. And then you divide that by 4 because you want 4 equal intervals. That means you go in intervals of pi 4s. So you start at pi 4s, then you add pi 4s, which is pi halves. and then 3 pi-4s, and then pi, and then 5 pi-4s. So these three in the middle are the x values that we're going to use. Okay? And so when we find the minus cotangent of x minus pi-4s, sorry, that's going to give us, so it would normally give us 1, 0, -1, but it's minus that. So that would be minus 1, 0, 1. And then when I add a -2 to that, that'll give me -3, -2, and -1. And those are my y values for my graph. All right, let me plot them here. So pi halves -3, that would be right here. And then 3 pi-4s -2. And then finally pi -1. So if I look here, here's the graph. And I went ahead and drew another one here. I'm going to draw another cycle of that. And you can just translate the points this way. So the values over here would be at 0, -1, at negative pi-4s, -2, and at negative pi-halves, -3. And you can see there that you get the other cycle of the graph. Remember to follow the procedure correctly and practice it, and you shouldn't have any issues.